So today we are going to have a look at the terminal equipment we need for communication. We need transmitters and receivers. Since we already learned the components we have available, we learned about semiconductors, about nonlinear processing components. We learned about filters, mainly frequency filters that we need for our communication. Now, today we are going to see how to assemble all these components into some useful equipment to perform useful communication. To start this discussion, we shall look at the brief history of radio communication. Because radio communication usually requires more complex terminal equipment than wired communication. But exactly the same principles as are being used in radio communications, as we shall see at the end of the second hour of today's lecture, are also being used in optical fiber communication. So are also used in wired communication. So it's all the same theory behind everything. So to see how radio communication started. Radio communication started with Hertz experiments almost 250 years ago. What did Hertz use? Hertz was the first to show the connection between low frequency electrical phenomena on one side and on the other side optical, so light effects on the other side, radiation propagation on the other side. So his experiment was assembled with, as a generator, Hertz used spark gaps. A spark gap connected to a half-wave dipole, actually starting the oscillation. The oscillation circuit, the tuned circuit, was the half-wave dipole itself. A spark gap here, high voltage was obtained through a low frequency high voltage transformer, but when the spark actually started here, it created a short here. So with a short, this behaved as a half-wave resonator, this dipole, and this resonator just ring out, and in that period of ringing of this resonator, it emitted some radiation with a wavelength that was short enough to be able to be in the far field region, in the radiation field region, inside the laboratory room Heinrich Hertz was doing his experiment. So his frequency was around 450 megahertz, wavelength 2/3 of a meter. On the receiving side, he also used a spark gap, but the spark gap used in a different fashion. So here the high voltage was actually obtained from the radio frequency radiation emitted by the transmitter. To get the highest possible voltage, he used a high impedance antenna, and that's a full wave dipole. To have the highest voltage here, and he accurately adjusted both the gap here to have the shortest possible gap to see the spark. He optically observed the spark here, and also he adjusted exactly the length of the dipole of both the receiving dipole and the transmitting dipole to have both dipoles on the same frequency, though the design of the dipoles is different. The transmitting dipole is a half-wave dipole, the receiving dipole is a full-wave dipole. What Hertz used were optical antennas, so-called optical antennas, so antennas made from converging mirrors. He could increase the range of his experiments by using both a converging mirror on the transmitting side and a converging mirror on the receiving side. Thinking about the geometry of his antennas, a cylindric mirror was the best choice here. He did a good choice here. Heinrich Hertz didn't know anything about other antenna types, but with these antennas he was able to demonstrate communication across a room, the room of the laboratory. He was able to demonstrate polarization of this radiation with a polarizer made of many parallel wires. He was able to demonstrate refraction of this wire on a dielectric prism. So he was able to explain everything that happened with light. He was do exactly the same experiment he was able to do with his device, though his device was powered by electricity and was emitting radiation at wavelengths corresponding what we call today radio waves or electrical world. The bandwidth of his communication was dictated mainly by the ring out time of a half-wave dipole, and here maybe we have a Q loaded of around 100 for a thin wire dipole, the same on the receiving side. So the bandwidth of his experiment was defined by the antennas he had, by the narrowband antennas. The same restriction applies today, so radio communication is mainly restricted to what antennas can do. Of course, radio communication went its own way now, and a very important contribution made by Nikola Tesla was to use resonant transformers, both a resonant transformer on the transmitting side and a resonant transformer on the receiving side. So what means resonant transformer? It means quite loose coupling between primary and secondary, but obtain a good, an excellent energy transfer by using a tuned circuit on the primary side and a tuned circuit on secondary side. Same on the receiving side, tuned circuit on the primary side, tuned circuit on the secondary side. On the generator side, the spark gap was in series with the tuned circuit, so this is exactly the equivalent of the Hertz transmitter. And on the receiving side, the tuned circuit was a parallel tuned circuit to obtain the highest possible voltage on the detector, because also Nikola Tesla didn't have good detectors here. He was really working in the near field. Nikola Tesla was working mainly in the near field. Other experiments discovered that working in the far field could obtain much larger range of communication here. But Nikola Tesla was mainly using the coherer, not the spark gap, the coherer. So breakdown between filings, oxidized filings of metal, is perhaps 10 times more sensitive than a spark gap. Soon after Tesla, other researchers found that crystals could make good semiconductor detectors, but these crystals, the lead sulfide, the galenite crystal, was very tricky, very unrepeatable. So some laboratory experiments could be done quite early, already at the end of the 19th century, but this was not a reliable detector. So Guglielmo Marconi relied on simpler magnetic detectors that were repeatable, that were reliable, that work reliably, until thermionics valves were invented. Thermionics valves that could approach, but still not yet reach, the performance of a semiconductor crystal. A much more important step was to have electrical amplification. Electrical amplification was first used in the regenerative receiver, invented almost at the same time by Armstrong in the United States and by Meissner in Europe. And the regenerative receiver could reach much higher levels of sensitivity. 3 orders of magnitude compared to 2 orders from 2 orders to up to 3 orders better sensitivity than could be done by direct detectors, because these detectors worked up to the thermoionic diode, worked without any amplification, while the regenerative receiver has amplification built in by the triode vacuum tube, invented by De Forest in 1907. Finally, the final thing that could be done in simple way was the super-regenerative receiver, invented by Armstrong in 10 years later in 1922. Here, with just a single vacuum tube, sensitivities in the order of 1 microvolts could be achieved. So much better than what could be done with direct detectors, and even direct detectors are much better than what could be done with the spark gap of Heinrich Hertz. So things really evolved in the range of the receiver, not just the transmitter. Spark gap had its own poor efficiency, but all these people use spark gaps. But on the other hand, the receivers were much improved. Much larger improvements could be seen here in the receivers. Let's see about the evolution of radio receivers. Say the receivers of Nikola Tesla and other experiments, Guglielmo Marconi, Chandra Bose, Jagadish Chandra Bose, Guglielmo Marconi, were all relied on direct detection with hopefully the best possible non-linear diode here to rectify the radio frequency signal into a low frequency audible signal here. The regenerative, here the Q was limited, the bandwidth of such a receiver. The Q loaded of this tuned circuit was around 100, because what the Tesla transformer actually used were air-wound inductors without a ferromagnetic core, and here the Q is limited to about 100. The Q loaded was maximum of 100. With the regenerative receiver used amplification with a vacuum tube and also regeneration, so part of the signal was fed back to the input circuit, and this could even make the circuit oscillate, but before the circuit oscillate, close to oscillation. A very high increase of the loaded Q could be obtained this way, because part of the loss in this tuned circuit was replaced by the feedback, the positive feedback, owing to the coupling between the two inductors. So the regenerative receiver was much more narrow band. Still, this corresponded to what the bandwidth was in the long radio wave, long frequency, long radio waves region in the kilometer range. This could be already useful in the medium wave range in the 100 meter range. 100 meter range, so could provide adequate selectivity to have the bandwidth of our receiver comparable to the bandwidth of the actual signal being transmitted. Thanks to the regenerative receiver also works as a Q multiplier. It multiplies the Q of a real tuned circuit by a certain factor provided by this feedback, by this mutual inductance from the output back to the input. Finally, it was again Edwin Armstrong, by careful observation, he noticed that when there were more receivers operating in close proximity, and one of the receiver was actually oscillating because the coupling between the output and input was set too strong, then additional signals appeared, and those additional signals appeared were radio frequency mixing. He could obtain sums and differences of different frequencies when close by receiver operated as an oscillator. So it was just a matter of design, electrical design, to actually produce a local oscillator with one of such oscillating receivers, and the other receiver acts as a mixer to convert this radio frequency signal down to an intermediate frequency. What is the advantage of doing this? Well, the first advantage was that amplification was much more readily performed at lower frequencies than at higher frequencies. So go down with the frequency, make a down conversion here, because those old vacuum tubes did not provide much gain at higher frequencies. So the vacuum tubes of 1918 could only provide some useful gain at low frequencies. The other important thing is now that the bandpass filter is no longer at the radio frequency, but it is at an intermediate frequency. So even if the same Q applies to this filter, because the filter is at a lower frequency, the same Q at a lower frequency, we can obtain a narrower bandwidth. So the bandwidth of the receiver now could be tailored to the actual received signal from the antenna. A detector followed and an audio amplifier also followed, because if vacuum tubes are available, they could also be used for audio frequency amplification here. Of course, the heterodyne receiver, or as Armstrong called it, super heterodyne, because some other guy already used the term heterodyne. This was a patent issue, actually. We call it today a heterodyne receiver. Heterodyne receiver, why? Because the local oscillator frequency is different from the radio frequency. The local oscillator does not operate on the same frequency as the radio frequency. We have also the homodyne receiver, when the local oscillator is at the same frequency as the radio frequency, but the homodyne is rather a broad term. We shall use other names for these receivers further on in today's lecture. The genius idea of Armstrong was to make a super-regenerative receiver. Where is here the trick? So in the regenerative receiver, this coupling adjustment to be close to oscillation but not yet oscillating was very tricky. This was very difficult to do. Though it could provide high Q, it provided high gain with just one vacuum tube of poor electrical performance. While if we build an oscillator that actually oscillates always, this oscillator could run all of the time, but we artificially turn on and turn off this oscillator. When I turn on an oscillator, the oscillator starts from whatever signal is present in the circuit. So if this is a negative resistor, so that it compensates for the losses in the tuned circuit, it will start from noise, or it will start from any weak signal that may be provided by the antenna. And now the oscillation that's actually growing here, the run-in of the oscillator actually grows the amplitude of this oscillation until saturation occurs. This actually provides gain. Gain because the same signal provided by the antenna is now amplified in overcoupled Q multiplier until saturation is obtained. As saturation is obtained, no gain is no longer provided here. So now it makes sense to turn off this oscillator and repeat the same sequence, because the process of gain, the gain process, is only available here. The typical figures are 100 megahertz for the radio frequency oscillator and 100 kilohertz for the quench oscillator. Operating at 100 megahertz with very old vacuum tubes, maybe just an oscillator could be built. So that's the reason why the poor components Armstrong had available was here. After this oscillator, this slope can be detected by the detector. The quenching frequency removed by a low-pass filter, and the resulting audio amplified or with a headset fed directly to a headset. This super-regenerative receiver only works with amplitude modulation, because with amplitude modulation the amplitude of this signal changes. If I change the frequency, the change is much smaller. The only thing I could do is perhaps slope detection, but slope detection is not very efficient. So after some time spent in saturation, possibly the least amount of time, the radio frequency oscillator is turned off. It rings out, but nothing interesting happens here until only the signal coming from the antenna remains after this exponential decay, and the whole cycle can be repeated. So such a super-regenerative receiver can achieve sensitivities in the order of 1 microvolt of the antenna, and this 1 microvolt is applied to hundreds of millivolts or even volts just in this oscillator. So I can obtain a gain of over 100 dB, plus I obtain automatic gain control, because this exponential slope is ideal an ideal automatic gain control. So everything with just a single vacuum tube, and the single vacuum tube can be also made self-quenching. So this second oscillator, it may require a separate tube, but it may also work with just the same tube, the same vacuum tube. Interestingly enough, today, this is 100 years ago, 1922. Today, we still use super-regenerative receivers in very simple circuits, like remote control for wireless weather stations, like remote control for car door opening, car unlocking, car locking. So these receivers are still being used in spite we have microprocessors with millions of transistors on a chip. This single transistor receiver, today is now a single, not a vacuum tube, a single transistor receiver, is still being used today. So the super regenerative receiver was such a clever idea that is still being used today. Though it is not a good receiver, but in many occasions, say short-range remote control, like car unlocking or wireless weather station with an outdoor sensor, this thing still provides very useful results for the price of one single transistor. Of course, much better results could be obtained with the heterodyne receiver. So we're going to look at the heterodyne receiver more in detail. So this is how a heterodyne receiver looks today. Today we have radio frequency amplification available. We can build mixers. We'll talk later on about mixers. We'll give mixers a detailed look into mixers. We can build filters for many different frequencies. What we are actually limited here, we are limited with that we need more than just a single filter. In simple receivers without the heterodyne principle, single tuned circuits or many of the same single tuned circuits could provide all the required selectivity inside the receiver. While in the heterodyne receiver, we have additional problems. And one problem that happens in a heterodyne receiver is that electrical mixing provides, besides the wanted response, also provides an image response at a different frequency. So, say if you have if we are receiving a 10 megahertz signal, radio we want to receive, we need a local oscillator that's offset by the intermediate frequency, but we have an additional response at some other frequency. So we do make our selectivity corresponding to our modulation bandwidth of the signal here in the intermediate frequency range. And this can be done because we are with Q loaded below 100. But we also need to remove this image. There are several possible ways to remove the image. One way is to simply filter it out with a suitable bandpass filter that is unrelated to the signal bandwidth, but it is only related to the distance of the image frequency. So here we see that the choice of the intermediate frequency is not completely free. We should be able to filter out the image response with the filter that we can make here. With the Q that we have available, the filter we can make here. And this is a typical choice for a shortwave radio receiver. This can be done, actually. These figures can be obtained. This is also Q loaded below 100, so can be done with a simple lumped component tuned circuits here. In order to make this receiver as user-friendly as possible, besides the main signal path to the receiver, we also have an automatic gain control loop here. So if the intensity of the antenna signal rises, the gain is automatically decreased, and this automatic gain control is applied may be applied both to the radio frequency amplifier and may be applied to the intermediate frequency amplifier, so that the whole chain here has linear amplification of the signal up to the detector, so that the amplitude modulation of the transmit signal is not corrupted here. So automatic gain control in the receiver, or automatic level control in the transmitter. These are also control loops that are not really required in theory, but in practice they are very handy, because we may receive stations with different power here, different signal intensity here. This signal intensity may be changing due to signal fading, especially in the shortwave region. Signal fading is common. So the user adjustments are now held to a minimum. The user only has to adjust the local frequency oscillator to tune in the station he wants. And that's all that needs to be done from the user side. Let's see now what the mixer is doing. This is a strange term. I introduced this thing. So the mixer is actually an analog multiplier. It's a circuit that multiplies two voltages and gives out the product, and this Km is the constant of our circuit here. So we build an electronic circuit that works as an analog multiplier. We multiply the input signal with the local oscillator signal. What do we obtain at the output? If we the intermediate frequency voltage, we get here the immediate value, the time domain immediate value is the constant of the multiplier, times the product of both voltages. So if we have a product of cosines, we could convert these products of two different cosines into a cosine of the sum of the two frequencies and cosine of the difference of the two frequencies here. So in this fashion, we actually obtain the sum of the two frequencies and the difference of the two frequencies here we obtain. So this circuit is actually producing the sum of the frequencies and the different frequencies. Spectrum-wise, if we try to draw the spectrum, we have the spectral line of the radio frequency signal, the spectral line of the local oscillator. We get the difference and the sum of the two frequencies. Of course, with frequencies, we are only talking about positive frequencies, and cosine is an even function, so the actual sign of this frequency under here doesn't matter, really. How do we do this in practice? In practice, we need a component, an electronic component that makes multiplication. And we may get multiplication in different ways here. We can use just a single nonlinear component, like a semiconductor junction, a semiconductor diode, that has its famous diode equation that includes an exponent function. An exponent function in mathematical theory includes all possible powers from 0, 1, squared, cubic, fourth power, fifth power, and so on. So if we develop this exponent function into a series, we obtain all possible powers of the applied voltage here. The square term is also responsible for multiplication, because the square term is square of the, if we apply two voltages, the sum of two voltages on the same diode, the square term will provide us the square of the first voltage, the square of the second voltage, and the product of the two voltages. So out of this term we may obtain also mixing. We obtain the squares themselves provide the second harmonic, but the product of the two voltages applies provides the mixing. These two terms of frequency mixing here. When our voltage is the sum of two voltages, the radio frequency voltage and the local oscillator voltage here. Of course, higher order terms provide higher harmonics, like third harmonic, like fourth harmonic, like fifth harmonic, and also provides higher order mixing terms. We will talk about these mixing terms on a future lecture, not today, because these mixing terms can also provide mixing, but can also provide us troubles. In such a single diode mixer, the only way we can extract the desired intermediate frequency is to use frequency filters, say tuned circuits for both the local oscillator, for the radio frequency, and for the intermediate frequency to be extracted out of this mixer. So this evolution of the response of the nonlinear component contains all possible terms. So we get from the DC terms up to the highest harmonic here. And we can only pull out the desired mixing product by using frequency filters with a single diode. And this is a single diode mixer or an unbalanced mixer here. This mixer is not balanced. We can do things better if we use single balanced mixers. So we use a diode pair to provide mixing, and this diode pair is fed in opposite phase with the radio frequency signal, but is fed in phase with the local oscillator. So here we considering the sense of these diodes. They are connected in series here. This one is inverted with respect to this one. The intermediate frequency signal actually sums from both diodes. The intermediate signal produced by both diodes sums, but the same circuit actually suppresses the radio frequency signal. Radio frequency signal is suppressed because of the symmetrical design of this diode. So we can suppress some of the unwanted terms here. We can suppress with a balanced design of the mixer. Here we can suppress the radio frequency signal. In this design with a variable resistor, junction FET or a HEMT used as a variable resistor, we can suppress the local oscillator signal, and we are only left with the radio frequency breakthrough, radio frequency crosstalk. Here we have the local oscillator crosstalk. We may also build a differential circuits from, say, bipolar transistors. We could do the same with FETs, and here we actually suppress the radio frequency signal. The radio frequency signal is suppressed. It cancels out in this symmetrical winding of this wideband transformer up here. But the local oscillator still has a crosstalk here through this circuit. So with a balanced construction, a balanced design of a mixer, a single balanced mixer is able to suppress one of the input signal, or the RF or the LO here. Of course, we can go further on and we use some double balanced circuits, like in double balanced mixers here. Here we use a diode ring, 4 diodes that are fed with opposite phases, both with the RF signal and with the local oscillator signal that are also fed with opposite phases here. Since this circuit is actually fed with opposite phases, on the intermediate frequency output we have very little radio frequency crosstalk because of the symmetrical design, and very little local oscillator crosstalk. The orientation of diodes is such that the intermediate frequency actually produced by all 4 diodes actually sums at the diode output. So we actually here with circuit design we sum the desired intermediate frequency signal, and we cancel out both the radio frequency and the local oscillator. We could do similar things without using transformers, because transformers are difficult to integrate in an integrated circuit. And this is a Gilbert cell mixer. A Gilbert cell mixer made out of 6 transistors, maybe bipolars, maybe FETs, actually cancels out with the symmetrical construction both the radio frequency signal and also cancels out the local oscillator signal, but the product of the 2 signals is available here. So the Gilbert cell mixer is also used for analog multipliers when they are used as multipliers, not as mixers. An analog multiplier may also be a modulator. A mixer is usually called inside the receiver. A modulator is the same circuit used in the transmitter. Doubly balanced mixers can be built in many different ways. Something most people forget about, that also an exclusive OR gate is actually acts as a double balanced mixer, because not the RF signal nor the local oscillator frequency can make any fit through the exclusive OR gate. And in fact, in some logic families, like in emitter coupled logic, the exclusive OR gate is actually built inside the integrated circuit as a Gilbert cell. So a Gilbert cell, vice versa, also operates as an exclusive OR gate in the logical world. So we have doubly balanced mixer, and finally the problem was image rejection. We always obtain here two frequencies, sum and difference. Is there any way we could remove this one of the two if we just want the sum, or if we want to suppress the sum and just want the difference? Yes, there is a solution called image rejection mixer. An image rejection mixer uses two multipliers, two identical multipliers with the same Km constant of the multiplier. And these two mixers are operated in quadrature. So with a 90-degree phase shift on one of the input signals, so with the 90 degrees delay, the cosine changes into a sine function. We calculate the output response, we develop out the output response, and then we also delay the output signal. Again, the cosine function changes into sine. We obtain here from these cosines, we obtain sines. Sines with a plus sign here, while here we obtain the minus sign. So if we sum this signal delayed by this signal, we only obtain the sum of the two frequencies at the output. The difference cancels out exactly if the circuit is ideal. What means if the circuit is ideal? That we have enough equal gain in both mixers, and that we have precisely 90 degrees phase shift here for the radio frequency signal, and precisely 90 degrees for the signal that has to be cancelled. This 90 degrees has to be accurate for the difference signal, because the difference frequency has to be cancelled out. We just want the sum of the two frequencies here. For the sum of the two frequencies also 90 degrees is desired, but is not as much as critical as for cancelling out the frequency we want to be cancelled. What can we, how much cancelling can we achieve in practice? With very careful design, we may achieve about not infinite cancelling like in theory, but in the practical world it's usually around 30 dB. In the best solution is around 40 dB. So also image reject mixers can be built, and we will see later on the application of image reject mixers. While for our discussion with single mixers, with block diagrams with single mixer, we are thinking about the double balanced mixer, because the double balanced mixer can suppress all most of the unwanted responses of the circuit, keeping just the desired multiplication of the two signals, the desired multiplication we want here in our circuit. So this is what the mixer is actually doing, and this is the kind of component we desire to have in our circuits. Let's see about things about transmitters. So transmitters, we only started our discussion with simple transmitter that could just be turned on or off with a modulator key. So here was a switch that actually powered the transmitter on or off. We would prefer to do better. And how to make a better transmitter also, considering the poor efficiency of the spark gap. Here perhaps only 1% of the low frequency power supplied to the circuit by the generator is by its power supply actually is transformed into radio frequency. So this is very poor. Maybe we can do better. And let's see how to do this thing better in building an AM speech transmitter. So a mechanical generator can be built up to perhaps 50 kilohertz. This 50 kilohertz is already long wave frequency range, 50 kilohertz equals to about 6 kilometers wavelength. So this is long radio waves. Although this was first built by Alexanderson in 1904, although Nikola Tesla achieved 15 kilohertz already more than a decade earlier, but he didn't use this generator much. Connecting this generator to an antenna, of course the generator itself is running all of the time, is not modulated, but if I put here a variable resistance, I can modulate this generator, and if this variable resistor is a carbon microphone, I can actually modulate the radio frequency signal produced by the generator by this carbon microphone. We can still do the same. This was the first speech AM transmitter, was built by Fessenden in 1906, allowing radio broadcast. We can also build the same today with just a single transistor, making a single oscillator, and modulating its supply voltage with a carbon microphone, acting as a variable resistor here. So a simple amplitude modulated AM transmitter built today is just a single oscillator modulated by a microphone. Because of this microphone is changing the voltage to the oscillator, also the parasitics of the transistor change, so we also get unwanted frequency modulation besides the amplitude modulation. Such a simple circuit also produces some frequency modulation. The same is true for other circuits. Even if we look 100 years ago, a variable resistor here will load the generator in a different way, and the RPM of this generator is going to change with this resistor because the loading is changing to the whole mechanical machinery here. So even this one has unwanted frequency modulation. These mechanical generators may look a thing of the past, of 100 years ago, very high frequency, but they are still alive today in quite a different form. An electromechanical radio frequency generator design survives today as stepper motors. Inside stepper motors, widely used in computer hardware like printers, like floppy drives, like disk drives, stepper motors use exactly the same design as these very high frequency generators, because they need to have a large number of poles to have small steps as small as possible. So this is where we find the same electromechanical design from 100 years ago today. But 100 years ago the idea was to make radio transmission with these motors. Today is the idea is to make stepper motors, but still a stepper motor today, if we turn its shaft with another motor, then we can produce quite high frequencies in the audio frequency and even in ultrasonic frequency range. So stepper motors, even today, they are useful as high frequency electromechanical generators. This is still alive. A more practical way of building an amplitude modulation transmitter is something that does not require complex mechanical devices, that can be built completely in an electronic fashion. So amplitude modulation today is still being used in the 120 megahertz frequency range, and this is used on board civilian aircraft. So it's still something that is alive today. How is such transmitter built? It starts with a crystal oscillator. Then we have frequency multiplier stages that include an amplifier in class C to produce lots of harmonics, and then extract the desired harmonic with a bandpass filter. This is a multiplier times 3, and we have another multiplier times 2 using the same design: a source of harmonics with a class C amplifier and a bandpass filter to extract the desired harmonic. And finally, we have to amplify the obtained signal, first with a driver stage in class A and then with an output stage in class C, to have both high efficiency but also to perform modulation here. Here we are actually calculating the multiplication between the input signal and the supply signal. We are actually having this class C amplifier also operates as a multiplier, as an analog multiplier we had here. So an analog multiplier may also be a class C amplifier. A class C amplifier that we have here. This class C amplifier. So we may have modulation in the radio frequency output stage. Okay, we have to modulate here with some power. The signal we provide here is DC power plus power at the modulating frequency. So we need quite a high power modulation amplifier here from the microphone to modulate the output stage of this transmitter. This audio amplifier and modulation transformer actually replace here the carbon microphone. The microphone can be now anything here. So we achieve modulation here in the class C output stage. This also operates as a multiplier. Why is this circuit still being used today? There's a good reason for doing so. This circuit, the circuit is connected to an antenna, but the antenna impedance may change. Say if this is a handheld transmitter, then the user may move this antenna and the antenna impedance changes. And the output stage should always provide the correct modulation. In this circuit, when we modulate in the output stage the signal, we obtain both high efficiency of converting DC power to radio frequency modulated power, and at the same time we obtain independence from the exact antenna impedance. So an automatic level control is usually not required in such a transmitter. So if we remove control loops out of our circuits, then this is certainly good. So an AM transmitter with output modulation is the usual solution, and the mating receiver, we already had it here. The mating receiver is a Heterodyne AM receiver with one frequency conversion, as we have on this schematic, or we may have more frequency conversions. If we have a higher frequency on the antenna, say 120 megahertz, then we first convert to a first intermediate frequency and then to a second intermediate frequency. I do not have a specialized drawing for this situation here, so we can do more than one down conversion using filters to have image rejection, or even using image rejection. Also image rejection mixers could be used. Image rejection mixer could be used. I can get rid of all unwanted responses, and I may have more than one down conversion in the receiver. In a typical aircraft receiver, I have 120 megahertz from the antenna, down converted to 10 megahertz. There's another conversion stage, mixing stage here, and then down converted to 444 kilohertz. That's usual intermediate frequency for AM voice communication. So in this way, we have found out what is the design of an AM receiver and what is the mating design of an AM transmitter. There may be more crystals for more channels in the AM transmitter, or in other words, also in the transmitter may use another form of frequency generator or frequency synthesis, but we are going to deal with frequency synthesizers at the end of this course, towards the end of this course, so not today yet. Today, understanding the operation of a transmitter power driven by a single crystal is completely enough for today. Next hour, we are going to look at even different kinds of modulation, maybe more efficient than the simple amplitude modulation, because the simple amplitude modulation, if we analyze the signal provided here, lots of power is lost in the carrier, and in amplitude modulation also the information processing is almost linear. So we may not have any gain of the signal to noise ratio here. So next hour we are going to look at different modulations to be more efficient, power-wise, to be more efficient spectrum-wise, and maybe to provide a better signal-to-noise ratio. But AM was being used for many years for radio broadcast, is still being used in civilian aircraft communication, is still being used in several other applications. So that's it for this hour, and next hour we are going to look at more complicated modulation schemes.